Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Hydrogen Atom from the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. First, we learn to reduce the two-body Schrödinger equation to an effective one-particle system. Second, we will know the nature of the effective potential consisting of the centrifugal part and the Coulombic part of the potential. We will also learn to solve the radial part of the Schrödinger equation subject to the admissibility conditions imposed on the radial functions. Next, we will derive the expression for the energy levels of hydrogen atom. Lastly, we will analyze the nature of the energy level diagram in terms of the degeneracy of the energy eigenvalues. So students, let us start with a basic introduction about the module. In this module, we will study the wave equations for a one electron atom, that is hydrogen, singly ionized helium, doubly ionized lithium, etc. So this is a two-body system consisting of the atomic nucleus of charge Ze and the electron of charge -e. So the potential corresponding to the attractive Coulombic force is an example of a central potential which depends only on the magnitude of the relative distances between the two particles. So for such spherically symmetric potentials, the Schrödinger equation can be separated in spherical polar coordinates. So here we shall first reduce the two-body problem to one-body problem. So the resulting equation involving the relative coordinates of the two particles has the appearance of the Schrödinger equation for a single particle of mass mu moving in a field represented by the potential Vr. So after separating the angular part of the eigenfunction, the radial part of the Schrödinger equation involves an effective potential consisting of the centrifugal term and the Coulomb potential. This equation is solved subject to the admissibility criteria on the radial functions near the origin and in asymptotic region. So the polynomial equation thus obtained gives us the final expression for the energy levels of hydrogen atom. Reduction of two-body problem to a one-body. So now let us consider a hydrogen atom, which is a two-particle system consisting of the atomic nucleus of charge Ze and a negatively charged electron moving under the influence of their mutual attraction. Thus, the wave function phi as a function of r1 vector, r2 vector, it is a function of r1 vector and r2 vector that is the position vector of the electron and that of the nucleus proton. So for a two-particle system, the two-body Hamiltonian can be written as H is equal to minus h cut square by 2m1 del 1 square minus h cut square by 2m2 del 2 square plus v as a function of r1 vector r2 vector, where the potential for the Coulomb force is given by v as a function of r1 r2 vectors equal to minus ze square by 4 pi epsilon naught multiplied by the modulus of r1 vector minus r2 vector equal to minus ze square by 4 pi epsilon naught r, where r is the separation between the two particles, that is the relative coordinate. The Schrödinger equation for the wave function phi r1 vector r2 vector is written as h phi r1 r2 vector equal to square bracket minus h cut square by 2m1 del 1 square minus h cut square by 2m2 del 2 square plus v r1 vector r2 vector square bracket close phi r1 vector r2 vector equal to tau multiplied by phi r1 vector r2 vector, where tau is the two-body energy. So now introducing also the center of mass coordinate capital R vector, which is defined by m capital R vector equal to m1 r1 vector plus m2 r2 vector, where capital M equal to m1 plus m2. So by writing del 1 vector approximately equal to del by del r1 vector equal to del r vector by del r1 vector del by del r vector plus del of capital R vector by del r1 vector multiplied by del r vector equal to del by del r vector plus m1 by capital M del by del capital R equal to delta r vector vector plus m1 by capital M delta capital R vector vector. Similarly, this delta 2 vector equal to del by del r2 vector equal to minus delta r vector vector plus m2 by capital M delta r vector. Now we express del 1 square by m1 plus del 2 square by m2 equal to del r square by capital M plus del small r square by mu. Now substituting these in the equation 25.3, we get minus h cut square by 2m del capital R square minus h cut square by 2 mu del small r the square plus v as a function of r vector multiplied by phi r small r vector capital R vector equal to tau multiplied by phi as a function of small r vector capital R vector, where phi r1 r2 equal to phi r vector and capital R vector and mu is equal to m the small m multiplied by capital M divided by m plus m. Since each of the operators on the left hand side of 25.9 depends either on small r or capital R, but not on both, a further separation of variables is possible in the form phi as a function of small r vector capital R vector equal to psi as a function of small r vector multiplied by chi as a function of capital R vector. Now substituting this in equation 25.8, we get minus h cut square by 2 capital M multiplied by 1 by chi multiplied by del square capital R multiplied by chi as a function of R plus minus h cut square by 2 mu multiplied by 1 by psi multiplied by del square R psi plus Vr minus tau is equal to 0. So since the first expression on the left hand side is purely a function of R and the second term is a function of small r only, we can put each of these equal to the same constant. We thus write minus h cut square by capital 2M del square R of chi as a function of capital R vector equal to E prime multiplied by chi as a function of R vector and minus h cut square by 2 mu del square R of psi as a function of small r vector plus Vr psi r vector equal to E psi r vector, where tau is equal to E plus E prime. Schrödinger equation for a single particle of mass. Equation 25.12a represents the uniform motion of the center of mass E prime being the kinetic energy associated with the center of mass motion. Now equation 25.12b represents the relative motion and hence depends on the internal structure of the atom and is the subject matter of the present study. So this equation has the appearance of the Schrödinger equation for a single particle of mass mu moving in a field represented by the potential Vr. So we have thus effectively reduced a two-body central force problem to a one-body problem. It may be noted that in this case, since the mass of the electron m is very much smaller than the mass of the nucleus or even than that of the proton in hydrogen atom, that is, the small m is very much less than the capital M. So the reduced mass, which is mu, equal to small m multiplied by capital M divided by small m plus capital M is approximated to small m. So since in the denominator there is a small m which is being very small, so it can be neglected. Effectively, it means that the nucleus is static and the electron is moving in the presence of Coulomb potential. So we are writing one body Schrödinger equation describing the relative motion as minus h cut square by 2 mu multiplied by 1 by psi multiplied by del r square minus ze square by 4 pi epsilon naught r, the whole multiplied by psi r vector equal to E psi r vector. Since the Coulomb potential is central, this equation admits the solution of the form psi NLMR equal to R NL as a function of small r multiplied by YLM as a function of theta and phi. Now here basically n we can write it by E, so we can write UEL as a function of R is equal to small r multiplied by REL as a function of small r, and proceeding exactly as in the previous module, the equation can be written as d square UEL as a function of small r by dr square plus 2 mu by h cut square multiplied by E minus V effective as a function of R multiplied by UEL as a function of small r equal to 0, where V effective as a function of small r equal to minus ZE square by 4 pi epsilon naught r plus L multiplied by L plus 1 divided by 2 mu r square is the effective potential. D square mu EL as a function of small r by dr square plus 2 mu by h cut square multiplied by E minus V effective as a function of small r multiplied by UEL as a function of r equal to 0, where V effective as a function of r is equal to minus ZE square by 4 pi epsilon naught r plus L multiplied by L plus 1 by 2 mu r square is the effective potential. Now in the latest slide is shown this effective potential for the case z equal to 1 and for the values of the orbital angular momentum number L equal to 0, 1, 2. So the solution of the radial equation energy levels, we now proceed to solve equation 25.5 subject to the condition UEL 0 equal to 0. We first introduce the dimensionless quantities, that is rho is equal to minus 8 mu E by h cut square to the power half multiplied by r, lambda is equal to ZE square by 4 pi epsilon naught h cut multiplied by minus mu by 2e to the power half equal to z alpha multiplied by minus mu c square by 2e to the power half. So this figure shows a plot of the effective potential for the case z equal to 1 and for orbital angular momentum quantum number L equal to 0, 1, 2. The unit of length is Bohr radius, where alpha is equal to E square by 4 pi epsilon naught h cut c is approximately equal to 1 by 137 is the structure constant, and let us remember that E is less than 0. In terms of these quantities, equation 25.15 becomes d square by d rho square minus L multiplied by L plus 1 by rho square plus lambda by rho minus 1 by 4 the whole multiplied by U EL as a function of rho equal to 0. So we begin by examining the asymptotic behavior of UEL rho. We observe that when rho tends to infinity, the term rho minus 1 and rho to the power minus 2 becomes negligible relative to the constant minus 1 by 4. Hence, for large rho, equation 25.19 reduces to the asymptotic equation d square by d rho square minus 1 by 4 multiplied by UEL as a function of rho equal to 0. So the solutions of this equation are proportional to exponential of plus minus rho by 2. Since the function is to be bounded everywhere, including at infinity, we have to retain only the exponentially decreasing function. Taking this factor out, we redefine the function UEL as a function of rho equal to exponential of minus rho by 2 multiplied by f rho. Indeed, for simplification, we write substituting 25.22 in 25.19, we get the equation for d square by d rho square minus d by d rho minus L multiplied by L plus 1 by rho square plus L by rho multiplied by f as a function of rho equal to 0. From our earlier study, let us recall that UEL rho and so f rho behave like rho L plus 1 in the vicinity of the origin. So factoring this factor out from the function f rho, we write f rho equal to rho to the power L plus 1 g rho. We write series expansion g rho equal to summation from L equal to 0 to infinity ck rho k c naught not equal to 0. Inserting 25.24 into 25.23, we get the equation for g rho, that is rho d square by d rho square plus 2l plus 2 minus rho multiplied by d rho plus lambda minus L minus 1 the whole multiplied by g rho equal to 0. Using the expansion 25.25 to solve this equation, we have summation over k equal to 0 to infinity over k multiplied by k plus 1 ck multiplied by rho to the power k minus 1 plus 2l plus 2 minus rho multiplied by k ck multiplied by rho to the power k minus 1 plus lambda minus L minus 1 multiplied by ck multiplied by rho to the power k equal to 0, or summation over k equal to 0 to infinity k multiplied by k plus 1 plus 2l plus 2 multiplied by k plus 1, this whole multiplied by ck plus 1 multiplied by rho to the power k plus lambda minus L minus 1 minus k multiplied by ck multiplied by rho to the power k equal to 0, so that the coefficients ck satisfy the recurrence relation ck plus 1 equal to k plus L plus 1 minus lambda divided by k plus L multiplied by k plus 2l plus 2 multiplied by ck. This shows that for a large k, we would have ck plus 1 divided by ck is approximated to 1 by k. This is the same ratio that we get when the series has the form rho to the power p exponential rho, where p has a finite value. Solutions reducing to a polynomial. Thus, in this case, we find that the function has an asymptotic behavior of the form UEL as a function of rho is approximated to rho tends to infinity over rho to the power L plus 1 plus p exponential of rho by 2, which is clearly not admissible. So the series 25.25 must therefore terminate, which means that g as a function of rho must be a polynomial in rho. Let us assume that the highest power of rho appearing in g rho be rho to the power nr, where the radial quantum number nr can be from 0, 1, 2, 3, etc. is a positive integer or 0. So then the coefficient CNR plus 1 equal to 0. From the recurrence relation 25.29, we have lambda equal to NR plus L plus 1. Let us introduce the principal quantum number n, that is equal to nr plus L plus 1, where n is a positive integer, that is it is equal to 1, 2, 3, etc. Since both n and L can take positive integers or 0 values, we thus see that the eigenvalues of equation 25.19 corresponding to the bound state spectrum E less than 0, they are given by lambda equal to n. Energy levels of hydrogen atom. Now replacing in 25.18 the quantity lambda by its value n obtained in 25.33, we get the bound state energy eigenvalues as En is equal to minus mu by 2h cut square multiplied by Ze square by 4 pi epsilon naught multiplied by 1 by n square equal to minus E square Z square by 4 pi epsilon naught A mu 2n square equal to minus half mu C square multiplied by Z alpha the whole square divided by n square, where n equal to 1, 2, 3 and so on, and alpha equal to 1 by 137 is the fine structure constant, and A mu denotes the modified Bohr radius, that is A mu is equal to 4 pi epsilon naught multiplied by h cut square divided by mu E square equal to m by mu multiplied by A naught, where A naught is equal to 4 pi epsilon naught h cut square by me square, being the Bohr radius. Striking features of energy eigenvalues. Note in the approximation m is very much less than m and A mu becomes equal to A naught. We note that since n can take on all the integral values from 1 to infinity, so the bound state energy spectrum corresponding to the Coulomb potential contains an infinite number of discrete energy levels extending from minus mu by 2h cut square multiplied by Ze square by 4 pi epsilon naught the whole square to 0. This is due to the fact that the magnitude of the Coulomb potential falls off slowly at large r. Another striking features which emerges from the result 25.34 is that the energy eigenvalues depends only on the principal quantum number n and are therefore degenerate with respect to the quantum numbers L and m. Degeneracy of the energy levels. Now the number n and are therefore degenerate with respect to the quantum numbers L and m. We have already seen that for each value of n, the orbital quantum number L can take the value 0, 1, 2 till n minus 1, and for each value of L, the magnetic quantum number M may take 2L plus 1 possible values ranging from minus L plus 1 till plus L. So the total degeneracy of the bound state energy level is therefore given by summation over L equal to 0 to n minus 1 over 2L plus 1 equal to 2 multiplied by n minus 1 by 2 plus n equal to n square. So while the degeneracy with respect to a quantum number is present for any central potential, the degeneracy with respect to L is characteristic of the Coulomb potential. Several properties of hydrogen-like atoms, like alkali atoms, etc., they can be understood in terms of the motion of a single valence electron in a central Coulombic potential at large distances, but it deviates as R decreases because of the presence of inner electrons. So this figure gives a sketch of the energy level band diagram of the hydrogen atom starting from n equal to 1 to n equal to 4. We have the energy corresponding to each quantum number, the principal quantum number basically n. Now using the spectroscopic notation, these levels are labeled by two symbols denoted by NL. The first one is the value of the principal quantum number, the second is the code letter used signifying the value of orbital quantum number L. So if we have a value of L equal to 0, then the code is S, L as 1, it is P, 2, then it is D, 3, then it is F, if it is 4, then it is G. So from the hydrogen atom spectrum, which has been discussed previously, we notice that the ground state n equal to 1 is a 1s state. The first excited state n equal to 2 is 4-fold degenerate and contains 1 2s state and 3 2p states m equal to -1, 0, plus 1. The second excited state n equal to 3 is 9-fold and contains 1 3s state, 3 3p states with m equal to -1, 0, plus 1 and 5 3d states with m equal to -2, -1, 0, plus 1, plus 2, etc. As far as the electromagnetic transitions from one energy level to another giving rise to the spectral lines, we will learn about this in the chapter on the interaction of electromagnetic field with one electron atoms. So students, let us summarize what we have learnt in this module. First, we have learned to reduce the two-body Schrödinger equation to a one-body particle system. Secondly, we know the nature of the effective potential consisting of the centrifugal part and the Coulombic part of the potential. Next, we also learned to solve the radial part of the Schrödinger equation subject to the admissibility conditions imposed on the radial functions. Next, we derived the expression for the energy levels of hydrogen atom. Lastly, the nature of the energy level diagram in terms of the degeneracy of the energy eigenvalues are being analyzed. Thank you.